A microprocessor is a computer processor that incorporates the functions of a central processing unit on a single or more integrated circuit (IC) of MOSFET construction. The microprocessor is a multi-purpose, clock-driven, register-based, digital integrated circuit that accepts binary data as input, processes it according to instructions stored in its memory, and provides results, also in binary form, as output. Microprocessors contain both combinational logic and sequential digital logic. Microprocessors operate on numbers and symbols represented in the binary number system. The integration of a whole CPU onto a single or a few integrated circuits using very large-scale integration (VSLI) greatly reduced the cost of processing power. Integrated circuit processors are produced in large numbers by highly automated metal oxide semiconductor (MOS) fabrication processes, resulting in a low unit price. Single-chip processors increase reliability because there are many fewer electrical connections that could fail. As microprocessor designs improve, the cost of manufacturing a chip with smaller components built on a semiconductor chip the same size generally stays the same according to Rock's law. Before microprocessors, small computers had been built using racks of circuit boards with many medium and small-scale integrated circuits, typically of TTL type. Microprocessors combined this into one or a few large-scale ICs. The first microprocessor was the Intel 4004. Continued increases in microprocessor capacity have since rendered other forms of computers almost completely obsolete, with one or more microprocessors used in everything from the smallest embedded systems and handheld devices to the largest mainframes and supercomputers. The complexity of an integrated circuit is bounded by physical limitations on the number of transistors that can be put onto one chip, the number of package terminations that can connect the processor to other parts of the system, the number of interconnections it is possible to make on the chip, and the heat that the chip can dissipate. Advancing technology makes more complex and powerful chips feasible to manufacture. A minimal hypothetical microprocessor might include only an arithmetic logic unit (ALU) and a control logic section. The ALU performs addition, subtraction, and operations such as AND or OR. Each operation of the ALU sets one or more flags in a status register, which indicates the results of the last operation, zero value, negative number, overflow, or others. The control logic retrieves instruction codes from memory and initiates the sequence of operations required for the ALU to carry out the instruction. A single operation code might affect many individual data paths, registers, and other elements of the processor. As integrated circuit technology advanced, it was feasible to manufacture more and more complex processors on a single chip. The size of data objects became larger, allowing more transistors on a chip allowed word sizes to increase from 4 and 8-bit words up to today's 64-bit words. Additional features were added to the processor architecture, more on-chip registers sped up programs, and complex instructions could be used to make more compact programs. Floating-point arithmetic, for example, was often not available on 8-bit microprocessors but had to be carried out in software. Integration of the floating-point unit first as a separate integrated circuit and then as part of the same microprocessor chip sped up floating-point calculations. Occasionally, the physical limitations of integrated circuits made such practices as a bit slice approach necessary. Instead of processing all of a long word on one integrated circuit, multiple circuits in parallel processed subsets of each data word. While this required extra logic to handle, for example, carry and overflow within each slice, the result was a system that could handle, for example, 32-bit words using integrated circuits with a capacity for only 4 bits each. The ability to put large numbers of transistors on one chip makes it feasible to integrate memory on the same die as the processor. This CPU cache has the advantage of faster access than off-chip memory and increases the processing speed of the system for many applications. Processor clock frequency has increased more rapidly than external memory speed, so cache memory is necessary if the processor is not to be delayed by a slower external memory. Special Purpose Designs. A digital signal processor (DSP) is specialized for signal processing. Graphics processing units (GPUs) are processors designed primarily for real-time rendering of images. Other specialized units exist for video processing and machine vision. Hardware acceleration microcontrollers integrate a microprocessor with peripheral devices in embedded systems. Systems on chip (SoCs) often integrate one or more microprocessor or microcontroller cores. Speed and power considerations. Microprocessors can be selected for differing applications based on their word size, which is a measure of their complexity. Longer word sizes allow each clock cycle of a processor to carry out more computation, but correspond to a physically larger integrated circuit dies with higher standby and operating power consumption. 4, 8, or 12-bit processors are widely integrated into microcontrollers operating embedded systems. Where a system is expected to handle larger volumes of data or require a more flexible user interface, 16, 32, or 64-bit processors are used. An 8 or 16-bit processor may be selected over a 32-bit processor for system-on-a-chip or microcontroller applications that require extremely low-power electronics or are part of a mixed-signal integrated circuit with noise-sensitive on-chip analog electronics such as high-resolution analog-to-digital converters, or both. Running 32-bit arithmetic on an 8-bit chip could end up using more power, as the chip must execute software with multiple instructions. Please subscribe, like video, share, comment and click bell icon for upcoming videos.